Welcome back to the channel. You might remember that in our last video, we used Newton's second law to discretize a string or chain like this and arrive at the equation below to predict the future location of a particle in the chain based on the locations of its neighbors. So this is a discretized representation of the wave equation, and it's called the Leapfrog algorithm. In this video, we're going to see how to implement this in Python using Numpy arrays and slice notation. We're going to focus in on just these last three terms in the equation to see in principle how the set of terms which represents curvature in the string can be described using Numpy arrays. So the Numpy or numerical Python module introduces arrays into Python. An array is like a list, except it's a list that you can do mathematical operations with. So we'll take this array, which has 9 elements, indexed from 0 to 8, and I want to note that the two extreme indices, the first and last, are not going to be modified, and that's for physical reasons. We see in the system we're modeling, we have a string fixed at both ends, so we're never going to update y0 or the last y. The convenient thing about arrays is that they allow us to do mathematical operations on every element at the same time, which can be quite quick. So if I take 2 copies of this array and shift one of them forward and one of them back, I can align the elements like so, and I can add them together. I can take 2 times the unshifted array and have the results land in an array that's waiting to receive the results. So here I have empty space waiting to receive between these 2 orange zones the result of this computation. I'm taking the first array plus the second array minus 2 times the middle array, which is what we have in the yellow here. And what results in this place is y3 minus 2y4 plus y5, which is exactly what we want. And notice that we have the same pattern in each column in this zone so that we can operate on the arrays, and it will give us the correct result in each location in our physical space. Taking a look at the pattern in these indices, I see that my first index here is 0, and my second is 6. The slice notation for this in Python is y of 0 to 7, and when I say 2, I mean colon. This might be frustrating that I want to go to 6, but I say 7. What it means is start at 0 and go up to, but don't include 7. Another way to express this is to notice that we count back from the end of the array 1, 2, and we can use negative indices to count backwards, so we could express this as y of 0 to minus 2. This means the same thing in this case. And if one of the bounds is 0 or the end of the array, we don't need to include it at all. So we have here on the right a more compact notation for this quantity. We'll stick with that. Now in my next array, I'm going from 2 all the way to the end, so we have kind of the opposite. Y of 2 colon says start at 2 and go until the array ends. Similarly, in our third case, we're taking 2 times the array and going from 1 to 1 short of the end. So that is 2 star y, 1 colon minus 1. So this expression is exactly what we want, but notice to simplify things, I left out the j indices, which represent time. Here we have just the spatial terms, but we can bring back in our past index, comma 1 for my second index in the array. Applying that pattern to all of the terms, this is what it looks like. I'm using a line continuation character here to fit onto multiple lines. That's the one case where Python does not care about indentation, is on the next line after a line continuation backslash. Here we have the tension and the linear density of the string, the discrete time step, discrete spatial step. So this is a single step. Notice the pattern here. Wherever I had an I in my initial algorithm, I replace it with a 1 colon minus 1. I plus 1 becomes 2 colon. And I minus 1 becomes colon minus 2. Now we've pushed the data forward one time, but we need to make space to repeat this procedure. So I'm going to push the present to the past, which looks like this. Notice I'm moving row 1 into row 0, and then move row 2 into row 1. It's important we do it in that order, otherwise we've overwritten row 1 before we were done using it. So we're using the curvature highlighted in yellow here to advance each position forward. And then we're pushing the data back. We want to plot what has happened, and then we will repeat this sequence again. Up next, we will code this together in Python and see how it works. Stay tuned.